guys, today we're going to be talking about the test for divergence. So typically we'll have a series that looks something like this. Okay, so we have to see if eventually the sums will diverge. That is, will they go all the way to infinity? The opposite of this would be convergence. Basically, the sums going to a finite number, adding up to a finite number over time when we go from n equals 1 to infinity. But here we're testing for divergence. So we typically use the test called test for divergence. So in this test, it states that if we have, so this is the series. So if we take an, which is the expression in the series, and we find that it is not equal to 0, it's anything other than 0. So whether it could be infinity, like does not negative infinity, infinity, some sort of finite number, then it shows that the series diverges. That's what the test for divergence shows. However, if we do get it's equal to 0, then we can't conclude that it's convergent. We can't conclude the converse. So if it's equal to 0, we're going to have to use a different test. So now let's start some examples. Alright, so say we have a series that looks something like this. N over each exponent of negative n minus 6. Okay, so we're going to see if this series is divergent. So to test for divergence, we are going to evaluate the limit at an, and this part is an. Okay, this part is in fact an because the form from before, as we mentioned, looks like this, right? So this part is an, and we're going to write that in here. So we're just going to copy it, write it right in here. Alright, so now what we do is we have to evaluate the limit. Oh, let's rewrite this as a positive exponent. It might help us. So this is the same as saying 1 over e to exponent n minus 6. Okay, so let's evaluate the limit. Well, we know that if we put infinity in to the numerator, it's going to become infinity. Because as n approaches infinity, this n also goes to infinity. Okay, same variable. Now, if we do it to the denominator, let's see what happens. So let's do that. So let's write it in for the numerator. And let's write it in for the denominator. Okay, so now let's see what happens with the denominator. So for the denominator, let's just do that separately. It might help. We are going to get... We're going to separate these two, so we can say that if we subtract it, we can separate it. Okay, these are part of the limit laws. And then we can see, oh, okay, well, if n goes to infinity and e to exponent n, we know the graph of e to exponent n looks something like this, right? So it increases as x increases, e to exponent x also increases, and it keeps going. So it goes to infinity. So that would mean that this bottom right here, you can think of it like 1 over infinity because e to exponent n is going to infinity. Well, usually people don't write this, but you can say that it's a very, very big denominator. Very, very big denominator. Very big denominator. So with a very big denominator and a very, very tiny, tiny one in the numerator in comparison, this limit is going to 0, and then this here, well, if we apply the limit laws, we just write 6 right here. So 0 minus 6. In this case, and it'll just be negative 6. So the numerator goes to infinity because as n goes to infinity, as said before, this goes to infinity, and the denominator is going to negative 6. So we're basically saying that this whole thing goes to negative infinity. That's what it's saying. And since the limit does not exist, because it's going to negative infinity, and it's not equal to 0, by the way, then we can say that the series is divergent. Series is divergent. And the original series was this, so we can say this series is divergence. Alright, so say we have another series right here, and now we have to see if it diverges. We're going to test for divergence, so we're just going to find the limit of it. So an is this expression right here, so we're just going to copy that. And then we're going to have to see, okay, well, we're going to have to evaluate this limit, and to do that, a very simple trick I like to use is I like to divide everything by divide the top and bottom by the same number, right? So like we're simplifying fractions. So we're dividing by n squared, okay? This is the highest degree here, highest power, see 6n squared and n squared, so we're going to do that. And here's what we're going to do. We're going to divide each term by it. That's basically the same as dividing each term by n squared. And then we see, oh, well, n squared and n squared, they cancel out to be 1, right? So we're going to write 1 right here, and negative 4 and over n squared. We're going to copy that for now. Minus 4 over n squared, all over 5 over n squared, plus this cancels out, just like we did here. So this is just going to be 6. And then we look at it and we say, oh, well, n goes to infinity, right? So this n squared is pretty big in comparison to n, right? N squared is really big comparison to 4. It's like the denominator of this fraction is exploding. So a very big denominator and a very small numerator, well, then it's going to go to 0 then, the whole thing in comparison. Same for this. So this is going to go to 0 as well. So we have 1 minus 0, this is 0, and this is 0, so minus 0. And then this is 0 plus 6. And then in the end, we get 1 over 6. 1 over 6 is a finite number. And according to a test for divergence, this is not equal to 0. As long as it's not equal to 0, we can use a test for divergence and conclude that it's divergent, that the original series is divergent. So therefore the series is divergent, since this limit is not equal to 0. So as long as it's not equal to 0, or if it's infinity, it still works because it's not equal to 0. Here's a very common mistake that people normally make. So if they have a series, let's say like this, okay, and they do this. Okay, well, I'm gonna find the limit. I'm gonna test for divergence. Okay, well, it's gonna make the denominator really big, so the whole thing's gonna be 0. Okay, well, 0. This is equal to 0, so we cannot use it. We can't conclude it's divergent. Then some people might think, oh, I'm gonna just say this is convergent because it's not divergent. So isn't the converse true? No, the converse is not true. In fact, this is actually a p series. This is a p series, and a p series with p equals 1, and so it makes it divergent. Well, that's a whole different story, but we cannot conclude this is convergent based on the fact that it's equal to 0. In fact, we have to use a different test. So if it's equal to 0, it can be either convergent or divergent. We don't know. We have to do a different test to find out so whether it is convergent or divergent. So you can see the test for divergence doesn't always work. It only works when the result shows that it is divergent. That means it cannot be equal to 0.